Chapter 3, Section 3 begins with the electromagnetic spectrum. The electromagnetic spectrum is the total range of electromagnetic radiation. You can see down here it varies from gamma rays through X-rays, UV, visible light, infrared, all the way to long radio waves. And the reason it's mentioned here is because electrons have properties of both individual particles and of waves. A wavelength is represented by the lambda symbol, which looks similar to an upside down Y. And a wavelength is just the distance between two consecutive peaks or troughs. So if you're looking at this diagram here, you could measure from peak to peak, that would be one wavelength, or you could measure from trough to the next trough, and that would also give you the wavelength. And since it is a length, it is measured in meters. Frequency is represented by a lowercase italicized v, and that is the number of waves that have passed a stationary point in 1 second. So it's waves per second, or we also say the units could be hertz. With the speed of light, we've mentioned this before with the E equals mc squared equation. We're going to be able to use it again here, where c is 3 times 10 to the 8th meters per second. And with this, we can have either frequency or wavelength and be able to calculate the other one. So for instance, in this problem here, I'm trying to solve for frequency, and I always have speed of light. That's a constant, 3 times 10 to the 8th meters per second. And by dividing that by my wavelength, given here as 7.6 times 10 to the negative 7th meters, that's going to give me the frequency of 3.9 times 10 to the 14th waves per second, or hertz. So then I would also expect that you would be able to calculate wavelength if given frequency and speed of light. A line emission spectrum is when you have distinct lines of colored light that are produced by excited atoms of an element that pass through a prism. So this middle row here is what a line emission spectrum looks like, and you can see there's some red, some yellow here, a couple different shades of blue, and a couple different shades of green, and a couple shades of blue that are seen. And this all comes from this original lavender gas. What was discovered, and this was in the late 19th century, was that when light passed through hydrogen gas and then was sent through a prism, it gave off this characteristic lavender light, and that lavender light through a prism split up into these various lines of the reds and yellows and greens and blues. And that was its line emission spectrum, and it was always that for that hydrogen gas. And when they tried different gases, it would give off different lines on this emission spectrum. So these are characteristic to each individual element. Quantum theory tells us the exact energy of an electron, but only the probability that that electron is in a particular region. It's very difficult to pinpoint both its location and its energy at the same time. So for instance, in this little diagram here, you can see the electrons, orbiting around the nucleus. Well, we can find out what energy level they're in, what orbital, but there's constant motion going on, so they could be at any location throughout that orbital at any particular point in time. And whenever an electron has a specific amount of energy, we call that quantized. There are 4 quantum numbers. The main one that we'll focus on is the principal quantum number, which is symbolized by an N. And this is going to be a value from 1 to 7. If you look on our periodic table in our classroom, they are labeled along with the periods on the periodic table. So 1 through 7 coincides with those periods on the periodic table. And that is the energy level where the electron is located. The shape is going to be the sublevel within that particular energy level. So it might be a round shape like the s orbital. It might be a figure 8 shape like the p orbitals, or more complex like the d and f orbitals. The orientation is going to be what orbital within the sublevel you're talking about. So how it is oriented around the nucleus, how that orbital is oriented, horizontally, vertically, and so on. And then finally, the spin refers to the electrons within an orbital. Every orbital can hold 2 electrons, but in order for both of those negatively charged electrons to fit in their orbital, they have to be spinning in opposite directions. So we say that one of them has a plus half spin and the other has a minus half spin. All right, so we've mentioned Dalton's atomic model, we've mentioned Thomson's atomic model, we've also mentioned Rutherford's atomic model. Bohr came along a little bit later, and this is about 1913 when he came up with his model, and what it says is it describes the electrons in terms of their energy states, ground states and excited state being the key ones. A ground state is going to be the lowest energy state that an electron could be at. That would be where it's most stable. And its excited state is any energy level higher than that ground state. So when we do our flame lab and we're going to heat up our chemicals, we will add this energy. Okay, we're adding thermal energy from the Bunsen burner. That will excite the electrons. They'll move up to a higher or excited energy state. And when they fall back down to their ground state, they will emit that extra energy in the form of light. And that light will be their characteristic color that if we pass through a prism, we could get its line emission spectrum from. So with Bohr, we really talk more about the electrons circling the nucleus in their orbitals or various energy levels. An orbital is a region of space where you can expect to find electrons of specific energies. The S are sphere-shaped, okay, like these ones here, and the P are dumbbell-shaped or like a 3D figure 8. And then D and the F are a little bit more complicated than that. The 1s orbital is going to be closest to the nucleus, 2s would be further out, and so on. Here are some examples of what p orbitals look like, and we mentioned how they're oriented with those quantum numbers. This is what I was referring to. Some may be vertical, some may be horizontal, and some may be through that z-axis. One of the principles that you'll need to know is called the Pauli exclusion principle, which tells us that no more than 2 electrons can occupy a single orbital, and then they must have different spins. That's where that plus half and minus half goes for. And that's what we represent by these little arrows here. This is one electron and this is the other electron. When doing electron configurations, it's important that you know which block of the periodic table that you're in. There are 4 blocks that coincide with the types of orbitals they have. The S block, which also includes helium, even though it's over here above the P block. The P block, the D block, which is in the middle of the periodic table, and the F block. Now, an electron configuration is really just a description of the electrons that are in an atom. Every element is going to have its own unique electron configuration. S orbitals are going to have only 1 orbital. P's will have 3 orbitals, D's will have 5, and F's will have 7. Now, if you look across a period on the table, you'll see that there will be an element added for every electron that is added to those orbitals. And remember, you can only fit 2 electrons within an orbital. So in the S block, for instance, there's only 2 elements across. So those 2 elements each add 1 more electron. So you get 2 electrons total, which is why you need 1 orbital to hold those 2 electrons. In the P block, you have 6 elements across, each adding their own electron. So in order to hold 6 electrons, you would need 3 p orbitals, each holding 2. With the D block, there are 10 elements across. So you would need 5 orbitals in order to hold all of those electrons. And then with the F block, there are 14 elements across, so you would need 7 orbitals in order to hold all of their electrons. Now, when looking at an electron configuration, you always start at the top left of the periodic table and you read straight across each row, just like you would the pages, the words and pages in a book, straight across until you reach whatever element that you're trying to get to. So for instance, this one here with fluorine, you would begin all the way at the top left, okay, and work your way through. You get to 1s1 here at hydrogen. 1s2 gets you to helium. Well, we're still not to fluorine, so we'd have to go to the second row. Lithium and beryllium would be next, so we're now at 1s2, 2s2, and then we'd move straight across into the P block, and that would get us to 2p. 1 would be boron, 2 would be carbon, 3 would be nitrogen, 4 would be oxygen, and finally 2p5 would be fluorine. And that's where we would stop if we wanted fluorine's electron configuration. Now when we write it, the first big number is going to be the main energy level, or the principal quantum number. So what period or row that it's in the periodic table. The next thing that comes is the letter. That's telling us what type of orbitals that it has. And the final thing is the exponent, and that's going to tell us how many electrons that we have. Now, orbital diagrams are very similar to the electron configurations, but they use lines and arrows instead of writing out the regular electron configurations with the exponents. So 1s would be represented by one line, and I would label underneath. If I was filling in electrons, I would do arrows up and down. 2p, I would draw 3 lines because there are 3p orbitals, and you label the middle one. If I was doing d orbitals, I would have to draw 5 lines. F's, you would have to draw 7. The Aufbau principle tells us that the lowest and most stable energy levels are filled first. So 4s comes before 3d. And we're going to label that on our periodic table. 4s is potassium and calcium, number 19 and 20. Then you start the D block, and that D block is the third D block row. So we go 4s and then to 3d and then back to 4p. And that's simply because 4s is actually a lower energy than 3d. And like I mentioned, we will be labeling that on our periodic table. Hund's rule tells us that orbitals are occupied by one electron before any pairing occurs. So you can see here, if we're doing these diagrams, this is carbon's electron configuration. The final part is 2p2. Well, we have 3p orbitals, and you're going to put one electron in each orbital, and then only when you have to pair them up will you do that. So even at nitrogen with 2p3, you can put one electron in each orbital without pairing them. If they have the same charge, they're not going to want to be next to each other. So only when you get to 2p4 will you have to start coming back and pairing up electrons. And finally, there are noble gas configurations, and this is essentially an abbreviated version of your electron configuration. So you will have to be able to do both the regular electron configuration and the noble gas. So be careful when you're reading directions. Only use the one that you're supposed to be using. So this one here is sulfur. Sulfur's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Well, if I'm doing a noble gas configuration, I'm going to look to the noble gas above sulfur in the periodic table. In that case, it's neon. I'm going to put neon symbol, Ne, in brackets, and then continue on with my electron configuration from there. So rather than starting all the way at hydrogen, I start at the nearest noble gas in the row above it. So neon's actual electron configuration is 1s2, 2s2, 2p6. So we just cut this whole portion out and simply put neon's symbol with the brackets and then finish the last part. So you can see how in some of the elements with the larger configurations that this would be a much simplified and shorter version of how to write the configurations.